hear me clearly? Yeah. So we are in the week 3 of our course. So last week we had discussions about interpolation functions, numerical differentiation, numerical integration, and a little bit of introduction to mathematical modeling and also uh, approximate solutions, like how to get approximate solutions to mechanical or like any structural problem, because we are dealing with structural mechanics or mechanical systems. So, like, we'll be analyzing those models. So, let's say if you have a beam or a bar or a complex structure, like some kind of a vehicle or a machinery in a factory. So, let's say if you want to, like, I'll just give an example. Like, uh, this might be uh, a civil engineering example, but like similar process can be followed for like any mechanical system or like any other system. So, like if you want to, let's say, build a structure like uh, bridge or a tall building, like with a lot of floors. So what we have to do? So initially we go uh, first we have to like go to the like area which you want to like build this, and you have to analyze all the uh, different aspects of that, like how much is the area and what is the strength of the soil, all these things. But like, but those are all things are fine, like we don't build it, like we don't look at that now. But after that, what you have to do, like what generally the procedure follows is like we have to design it. So we have to design the structure such that it will be able to withstand all the forces, withstand all the forces or load that it will experience during its operation. So it's like before constructing the building or any like a bridge, we estimate the amount of traffic it will like amount the amount of the traffic it will experience, like how many vehicles will pass through it, like if there are maximum number of vehicles passing with some kind of speed, how much load will act on the bridge. And let's say if there is a building, if the building is designed, like we'll design the building for different categories. Maybe like it's, if it is a commercial building, these many people will come due to the amount of people coming to it. Like you estimate the load. So then after estimating the load, you try to design a structure. Like let's say you just assume the bridge as a beam, like a beam. So initially you design with some like uh, you take some thickness of the beam, and you will apply uh, like the load you have estimated, like let's say some kind of load you have estimated, and you try to look at the internal forces or the stresses or the deflection experienced by the bridge, or in this case, a beam. So, what is this called? We call this as analysis. So, analysis of the structure, or you can say also structural analysis or something like. So, you try to analyze the structure. So, if you see that the structure is like behaving weirdly, or if it is going like bridge is bending too much because of this thickness, what you do, you go and like increase the thickness of the beam and again do the analysis. So like that, repeated cycles of analysis go on during design. Like design is not like a simple problem. Like if you want to design any structure or any machinery, like it will be a iterative process, trial and error process, kind of a trial and error process. You go through analysis, you go like design and analysis, like it is kind of a loop. Like repeated times we have to do the analysis. So in order to do the analysis, like whatever the physical structure we have to model it like a mathematical model. Mathematical model is necessary to do the analysis. So anything, any structure which you have to somehow bring down and construct a mathematical model of it. Like you have to make you have to take some kind of conditions like uh, what do you say, conservation of energy, conservation of mass, conservation of uh, momentum. You take all these kind of laws and you get a mathematical model. So mathematical model is nothing but finally we get some kind of differential equations or partial differential equations. So most of the mathematical models has differential equations, at least in this context of structural mechanics or this structural analysis. So these differential equations, they give the cause and effect relationship. So what is the cause? Cause is the load, like load, and effect is some kind of you can say stresses experienced or the deformation you can say. So depending upon the load or the forces experienced by the body, we get the deformation or the stress, whatever it is there. We estimate this based on the mathematical. This from cause to effect, we go by solving the mathematical model. Okay. But the thing is, let's say I have a bar like this. Uh, some bar is, so I have some bar like this, and let's say this bar has a cross section area. A is the cross section area of the bar, and let's say L is the length of the bar, and there is some kind of distributed load, like axial distributed load. So this is kind of load per unit length, Q acting on the bar. Okay, or you can also call it as surface traction. So like if you do the, like if you want to, like let's say if you want to find out the mathematical model of this bar, you can like take a simple small element like this, a small element of, let's say, length dx, and you take some kind of reaction forces. Like from here, if I am taking, this is the small element, I'm cutting out this element and I am taking this element. So this will have some kind of load here, and there is also some inertial force. Like if the force, the Q which is acting is time dependent and has high frequency, then there will be also an inertial force. So if we take the equilibrium of this and uh, integrate it over the whole length of the bar. Finally, like I'm not doing it. Like if you want, you can go to the notes, FEM1 file, like which was uploaded in the class. So we finally get differential equation of the form, which is dou by dou x into dou by dou x of EA into dou u by dou x plus q into rho a into dou square u by dou t square. So this is famously known as the wave equation also. Like you can also call it as a wave equation, or here in this case, like governing equation of the bar, or the equation of motion of the bar. All are synonymous things. Let's say like the force is not time dependent, or like let's say uh, the inertial effects can be ignored, like this term can be ignored, then we will be left with d by dx, because earlier u was function of both distance and also time. Now I am saying that u will not be dependent on time because I'm ignoring the inertial effects. So now u will be only a function of x. So that's why I am taking here ordinary differentiation from partial differential equation. I'm taking only ordinary differential. So this will be my governing equation. Okay, and this equation is valid over the domain of the bar, which is, look, domain is like over the length of the bar here. So domain is nothing but over the whole structure. So here the bar has a one-dimensional, bar is a one-dimensional structure. So I can say domain is x belongs to 0, comma L. So x varies from 0 to L. Okay. So this is the domain of the bar. So, and we also need, like if I want to solve this, we also need, along with this, boundary conditions, governing equation plus boundary conditions to solve this problem. So, like you want to analyze this bar, like for some kind of load Q acting on it, you want to see how much the bar is deforming. So we have the governing equation and we have the boundary conditions. So in order to get displacement, what should we do? We just simply integrate this. So if you integrate this once, you will get EA into du by dx plus ux plus C1 is equals to 0. So I'm just integrating it once. Integrating. Now again I'll integrate this because this is still du by dx. I want u. So u is the solution which I want to find out. So I will again integrate this. Now I will get q into x square plus c1x plus c2 is equals to 0. Okay. Let's say the bar is fixed on both sides and there is some load q per unit length acting. So now you can see that there are two boundary conditions. At the left end, at x is equals to 0, u is 0, and at x is equals to L, u is 0. So these are my two boundary conditions. So I have here two unknowns, right? So C1 and C2. So I can just substitute x is equals to 0 in this. So this u is nothing but u of x here, okay? So u of x, you can write, or now substitute x is equals to 0. So this term will become 0. C2 will come to like this. So you will get C2, u of 0 is already 0. You will get C2 is equals to 0. Now again, here I'll substitute C2 is equals to 0. Now I will take u of L is equals to this. C2 is already 0. I'll get C1 is equals to P into u of L plus q L by 2. So u of L is 0 again. So this is minus. So C1 is equals to minus q L by 2. So now I substitute both C1 and C2 in this. I substitute this, I'll get VA into u of x plus q into x square by 2 plus C1 is qlx by 2 plus yeah, this is VA by L. Okay, fine. Anyway, it becomes 0. So minus qlx by 2 is equals to 0. So now I rearrange this. If I rearrange this, I'll get something like q by 2 into x minus L. X minus, I'll take qx, okay? X minus, yeah, L divided by E. So this is my solution. And this is the deformation experienced by the bar. Deformation experienced by the bar due to applied load Q. So you substitute, like if you want to, let's say, like you can see that if you substitute x is equals to 0 here, you will get uh, u of 0 is equals to 0. If you substitute x is equals to L here, you will get again this as 0. So this solution is satisfying the boundary condition. That is the first thing we have to look at. So, and then if you want deformation at any other point, you can just substitute x, like what is the value of x, and you will get the deformation at that point on the bar. So this is nothing but the analytical solution of the bar. Okay. So this is analytical solution or closed form solution. You can also call it as closed form solution. So you can see that this is a very simple problem. We are just integrating this governing equation two times and applying the boundary conditions. We are getting the integration constants and finally we are getting the solution. So this is called as analytical solution because like you are integrating directly and you are getting a closed form solution. But what happens is that many times, like here, the bar domain is a simple like line. So x is equals to 0 to L. This is a 1D problem. Like if if you go to like lot of mechanical like or buildings or structures, like they will have like a very irregular uh, domain like this. I don't know. I'm just randomly drawing. Like you might have some kind of domain like this. So for this, if you want to integrate, like it becomes cell. Like you cannot analytically integrate them. So somehow we have to go and do numerical integration. So, or numerically, we have to solve these problems. Like numerically, we have to solve the governing equation and get some approximate solution which is near to this analytical solution, but like not exactly equal to the analytical solution. So that's what we are dealing in this course. So one of the ways of getting approximate solutions is method of weighted residuals. Weighted residue. Okay, so let's see how we can use the numerical methods or approximate methods to get a solution which will be near to the analytical solution, but not like exactly equal to that. So since an analytical solution is not always possible, we seek an approximate solution. Let's call that u hat of x. So this is approximate, which will be nearly equal to our exact solution, which is u of x. So this approximate solution will not perfectly satisfy the governing equation. It will approximately do it, but not perfectly. or also like boundary conditions. Some boundary conditions it has to exactly satisfy. Not all boundary conditions. We will see what are those. So because it doesn't satisfy exactly the governing equation or the boundary conditions, so it will have some kind of error. So it will lead to some errors. Obviously, because this is approximate, it will lead to some errors. So we can call those errors as residuals. Okay? Because it is left something like which is left after doing or like filtering or something, we can call it as error or a residual. Okay, so there can be two kinds of residuals, like because the governing equation is not being satisfied perfectly. Like this is the governing equation, right? D by dx of EA into D. This is I am substituting U hat here instead of U because I am taking the approximate solution plus Q. This is not exactly equal to 0. That's why it will be having some value like near to 0. Like let's call it R omega, which is you can call it as domain residual. You can also have some boundary condition residual also, which you can use this operator M u cap plus R. Like we will see what is this like, but uh, like if you have a forced boundary condition, there can be some error there also. So this is a boundary residual. Like if you have some kind of force at the end of a bar, like which is like Q, you can write it as EA into dou U by dou X at X is equals to L is equal to Q. So this, like if you substitute U cap here, this will become dou U cap du cap by dx minus Q at X is equals to L is it is not equals to 0, but it is having some kind of error. We can call it as boundary residue. So that's what approximate solution leads to error. So, but we can always reduce this error. So how we can reduce this error? So there are ways to do that. One way is using the method of weighted residuals. So weighted residuals is nothing but we are taking the error and we are trying to minimize it in average sense. Okay. So over the whole domain, you try to minimize the error in an average sense. Okay. This you can take it as W dash R omega D gamma R gamma. So this is gamma is equals to 0. So it is nothing but like because this is a like continuous domain, like integration is nothing but summing, right? Like integration is nothing but summation. You can also write this as like this W1 R1 plus W2 R2 like this. But because this is a continuous domain, like you can write this summation as integration. Okay. So average means like there is also something like below this like divided by like integration integral like this also you'll get, but there is like zero here already. Like if you send that this side, like it will get multiplied with zero. So it's not required. So we are trying to like average out the errors. So like we are trying somehow we want to make that errors are like uh, r omega and r gamma should be minimized in an average sense. Should be minimized in an average sense. Let's say like you will have like uh, let's say this is your this is a beam. This is a beam, fixed beam, and this is the actual deflection of this beam. But after doing it, like you might get like after taking some approximate solution, you might get some error. Like you might get some curve like this, and there is some error. So like if you take this error at each point, like continuously over the domain, and if you give some weightage to each error and do this integration, like you are somehow averaging out the errors and making uh, the error minimized in an average sense. So you can read more about minimization of residuals or like weighted residual, or like if you are all like if you are already familiar with least squares approximation, that is also a similar thing to do. Like instead of w, you will take r omega. So r omega square, like then it becomes a least square problem. Yeah. So this is nothing. This is called as the weighted residual method. So like as I said, like we have to assume something. Like we have to assume the solution. We have to assume the solution before like doing this all these things. Like you can assume the solution like a polynomial like this a naught plus a1x plus a1x square, or you can also assume it as a trigonometric form like something like this c1 uh, sine pi x uh, plus c2 sine 2 pi x, something like this. You can assume it and you substitute in the governing differential equation, and then you do this weighted residual minimization. You will get the values of this a naught a1 a2 or c1 c2, like whatever the constants are there in your approximate function, those coefficients you will get. So if you get those coefficients and put it here, that will be your approximate solution. So like only thing which we have to estimate is this coefficient. So like in approximate methods, the problem boils down to finding out these coefficients. So in like weighted residual, there are like two forms which we can use. One is called as strong form, and other is called as weak form. So we will see what is the strong form and what is the weak form. So like let's take the domain residual. So domain residual will be equal to, like let's say domain residual is equals to 0. You have some thing like this wj, like take w as wj, like some weighting function you will take. This also we have to assume something. So like the solution which we are assuming, w also we have to assume something, and take the domain residual, and let's say this is equals to 0. For a bar problem, the domain is like we know it is from 0 to L, and it is a one-dimensional domain. So only one integration is required. Later we will see if we go to 2D, this will be a double integration. And if you go to 3D, it will be a triple integration. So the domain residual is dy dx of EA into d u cap by dx plus q into dx. So this d omega becomes dx because this is a bar problem and this is a one dimensional domain. So this is the so this is nothing but the strong form, and here you can see the uh, the approximate full function u cap is differentiating, like it is getting differentiated twice. So whatever the u which we assume here, like if we are solving with this strong form, we have to make sure that u cap is u cap is at least differentiable two times. Like let's say if you take let's say if you assume u cap is equals to a naught. So if you differentiate it, du cap by dx is equals to 0. So this you cannot take because this is not differentiable. Now let's take u naught is equals to a naught plus a1 x. Now if you differentiate it once, you will get a1. But again, if you differentiate it again, second time if you differentiate it, you will get 0. So this also you cannot assume. So we will add another term, a naught plus a1x plus a2x square. So now if you differentiate it, you will get a1 plus 2a2x. And again, if you differentiate it twice, you will get 2a2. So this is differentiable, like this function a naught plus a1x plus a2x square, which is a second degree polynomial, can be taken as an approximate solution here for this strong form. So you can see that like the polynomial degree requirement is 2 here. Now let's do some integration and see what like how can we reduce this second degree requirement to a first degree requirement. Like instead of taking a second degree polynomial to approximate the solution, like if we just take a first degree polynomial, it will be computationally very less expensive and efficient. But to do that, we have to do some steps. Like if you have this strong form of the residual, like applying integration by parts, like we will apply integration by parts. We will get something like this. So you take this breakdown into two terms and you apply integration to the first thing. You will get wj into ea du cap by dx 0 to L minus, and this will be integral 0 to L dou by dou x ea into dou u cap, right, dou x, and this will remain same, u dx is equals to 0. So now you see here, just by integrating this strong form, you can see that now the different now the if you see this differentiation of u with respect to x in this whole equation, you can see that u has only one differentiation. So here in the above equation in the strong form, u was getting differentiated twice, but here it is only getting differentiated once. So instead of taking a second degree polynomial, I can just assume a first degree polynomial a0 plus a1x. I can assume this as the solution. And now you can see the differentiability is getting satisfied by a lower degree polynomial compared to a strong form, which was like which the requirement for the strong form was like we should have a second degree polynomial at least. Here, the first degree polynomial is the least required approximation which we can take in the weak form. So this that's why like we are weakening the requirement differentiability requirement of the solution. That's why it is called as weak form. Okay, so this is called the weak form. So weak form, what it does is it reduces the continuity requirement. Continuity requirement of approximate solution because only its first derivative needs to exist. So this is called as the strong form and the weak form. So in finite element, we always take the strong form, do integration by parts, and get the weak form. And from that weak form, we try to get the like we assume a solution and we get the coefficients a naught and a1. Like in all these methods, like whatever we are going to see in the future for finite element method, we always take the weak form, like we always take the strong form, then we integrate it by parts, get the weak form, and then do the further process. So we deal with the strong form because it will lead to more conditions to the solution. So that's why like it is always becomes easier to deal with the weak form. Okay. So in any problem, in any finite element problem or a structural problem, there are two kinds of boundary condition. So one is essential boundary condition. So essential boundary conditions are nothing but the boundary conditions which have to be satisfied by the approximate like the primary variable. Okay. So let's say if your bar is there, if your bar is fixed on one end, okay, your bar is fixed on one end. So u of x is equals to 0 is equals to 0. So at x is equals to 0, the displacement or the deformation of the bar is 0. So this has to be satisfied by your approximate solution. No matter whatever the approximate solution you take, this condition should be satisfied. Or you can also call it as Dirichlet boundary condition. Okay. So this has to be satisfied in any form. So these are imposed on the primary variable. primary variable is nothing but the deformation u here. So deformation or the displacement u. Displacement u. Okay. So for example, here u of x is equals to 0 is the essential boundary condition. So let's say if I assume some function like u of x is equals to c1 into sine phi x by 2, something like this. So if I put u of 0 is equals to x is equals to 0 here, now I can see that this will become 0. So this you can call it a admissible kinematically admissible function, kinematically admissible approximate function, because it is satisfying the essential boundary condition. So whatever the approximate solution you take, it has to be kinematically admissible. Kinematically admissible means it has to satisfy the essential boundary. Like let's say if you take q of x is equals to a naught plus a1x, something like this. Then you can see that if you substitute x is equals to 0 here, then you will get u u naught is equals to u hat of 0 is equals to a naught. So if this a naught is equals to 0, if a naught is equals to 0, then it is a kinematically admissible. If this a naught is not equals to 0 and if it has some value, then it is not kinematically admissible. So essential boundary condition has to be satisfied anyhow. So the conditions, the boundary conditions on the primary variable. Primary variable is nothing but u. So whatever like you are solving for. So displacement is something which we are solving for here. So that is our primary variable. Imposed on this primary variable, boundary conditions imposed on this primary variable are called essential boundary conditions. Now let's see what is a natural boundary. So natural boundary condition, or you can call we can also call it as Newman boundary condition. Newman boundary condition. So these are related to secondary variable. So these are related to secondary variable. What is a secondary variable? We will see. Secondary variable is nothing but traction. Let's say traction. So you can see this is a derivative. Primary variable is nothing but a derivative of the primary variable du by dx. So related to this, if there are boundary conditions, like let's say there is a force acting on one end of the bar, then you can say this is nothing but EA into dou u by dou x du by dx at x equals to L is equals to Q. So this is a traction boundary condition or also natural boundary condition. You can also call it as a human boundary condition. So in the weak form, you can see that this will come. So if you take this in the like if you take this term of the weak form, which is nothing but wj into dou u cap by du cap by dx 0 to L, and like if you substitute it, if you substitute like something like here x is equals to 0 and E cap by dx, x is equals to L. You can see that here, this is nothing but if there is a load acting on the bar, this will become equal to Q. Okay. At x is equals to 0, we make sure that uh, W of j becomes equals to 0. So this will become automatically 0. So natural boundary condition automatically comes in the weak form of the uh, uh, weak form of our governing differential equation. So we don't need to take care of this weak form. Like we don't need to take care of this natural boundary conditions while we are choosing the approximate solution. While we are assuming the approximate solution, we don't need to worry about the natural boundary condition because this is naturally satisfied in the weak form of the governing differential equation. Okay. So that's why this is called as natural boundary condition. So we should always see that essential boundary condition is satisfied by the approximate solution which we are assuming. Natural boundary condition will be taken care in the weak form. So we don't need to satisfy our approximate solution which we are assuming doesn't need to be satisfied by the like it doesn't need to satisfy the natural boundary condition. So that is the essence. So the method of weighted residuals which we have seen. So there is also some like if you take this assume this solution and if you put it in this if you put it in this integration by parts, like if you assume W also something and you do the integration and like you will get two equations, and if you solve that you will get C1 C2. That is like a very simple process. So you can see the example in the class which was solved, and you can do it. Like now the problem like is like becomes very simple. You just have to get the integrating constants. Like if you are assuming the approximate solution as u naught plus a naught plus a1x is equals to 0. So we have to find out what is a naught and what is a1. So that can be find out very easily, and there is like not a very difficult process. But I wanted to revise whatever was weighted residual. What is the weighted residual method, and like this is the whole essence of weighted residual method. So this is like weighted residual method is one way to get the weak form of the one way to go to the weak form. Like we can also go through something called like variational. We can also use variational principle to do that. So but today we will not look at that. Like but let's see this question. So like if there are like these two kinematically if there are these two bar problems, so like A and B, there are two bars. Like so sorry, this is a bar and this is a beam. So beam is nothing but it will go transverse displacement like this, transverse deformation, and bar is something which will go deformation. So I'm just applying a tension force. So bar will elongate along its length or compress along its length. So beam will undergo transverse deformation. So for these two, we have to find out kinematically admissible forms of kinematically admissible forms of shape functions, or you can also call solutions, kinematically admissible solutions. And like for each case, we have to find out two solutions. Like we can approximate, like there can be n number of approximate solutions which you can assume, but here I'm just asking two solutions. which can be the solution of these problems. So the first thing is important thing which we should remember is the solution assumed solution solution assumed should be kinematically admissible. Okay, what is meant by kinematically admissible? What is kinematically admissibility? Anyone wants to like take a guess, or like if you have listened to the class and if you have uh, read the notes, anyone? Boundary condition, yeah. Kinematically admissibility is nothing but boundary condition should be satisfied. Not all the boundary conditions, essential boundary conditions should be satisfied. Essential boundary condition. Essential boundary. Okay. Now let's like take uh, some approximate. Let's define what are the boundary conditions here. First, we will take the bar. So this is the bar, right? This is the bar given, and x is starting from here, and it is going in this direction. And there is a load applied to the bar, which is u. Like there is some value to it, but like here it's not required. There is some length of the bar. So here you can see this bar is fixed at the right end. So x is starting from here and it is going uh, in the uh, right direction. So the positive direction x is going. So here uh, the here the domain starts from x is equals to 0, which is the free end, and x is equals to L, which is the fixed end of the bar. So at this end, the displacement of the bar or the deformation of the bar is 0. Okay. And at this end, at the free end of the bar, there is a force, which means this condition at x is equals to 0 is 0. So this is our essential boundary condition here, because this boundary condition is on the primary variable, which is u, essential boundary condition. This boundary condition, you can see this is called as Newman boundary condition, natural boundary condition, or transverse boundary condition, because this is a boundary condition imposed on the secondary variable. So this is natural boundary condition. So our approximate solution should satisfy only this boundary condition. So whatever which we are assuming, like the assumed solution should satisfy only this boundary condition, which is this our essential boundary condition. Okay. So let's say I want to let's say I want to uh, satisfy the I will take some kind of like higher polynomial. Like I can assume, let's say phi of x is equals to c1 into x minus L plus c2 into x minus L whole square. Is this satisfying the essential boundary condition? Yes or no? Anyone would like to answer? We have
Yes.
yeah, it is satisfying, because if I substitute x is equals to L, if I substitute x is equals to L, I will get phi of 0 is equals to 0. Now I'll take, let's say, phi of x is equals to c1x plus C2 x square, something like this. Will it satisfy? Will it satisfy the essential boundary condition? No. Very good, then. So this will not satisfy the essential boundary condition. So this is a one kinematically admissible function or solution which can be considered. Now let's assume some trigonometric form of solution. Let's say if I have uh, phi of x is equals to like something like c1 into cos pi by 2 into x by l, pi x by 2l plus c2 into cos uh, 3 pi by 2 into x by l, like this. So will it satisfy the boundary condition? Will it satisfy the essential boundary condition? Will it satisfy? Yes or no? Anyone? So the essential boundary condition is u of l is equals to 0. So if you substitute l x is equals to l, this should become 0. So will it satisfy or not? I use a thicker. Yes, it is satisfying. It does. Because if you substitute x is equals to L, this will become cos 90 and this will become cos 270. So cos 90 and cos 270 are 0. So our we can assume this as our approximate solution. We can assume. So this satisfies. Let's take some other thing like I'll take sine. Instead of cos, I'll take sine. Sine 3 pi x by 4. Will this satisfy? No, because if you substitute x is equals to L, x is equals to L here, you will get the sine 90, which is 1, and here you will get sine 270, which is minus. So this will not be equal to 0. So this is not satisfied. So not kinematically admissible. So we cannot assume this as our approximate solution. Okay. Uh, this second structure, which is a beam, it's a cantilever beam. So we have not gone deeply like into beams in this week, but let's see. Like if you have a beam like this, and there is some kind of load acting on it, and the length of the beam is L, and there is Young's modulus of this beam material is E, and I is the moment of inertia of the cross section of the beam, uh, and like X is varying from left to right. So what can you like? What can you guess about for a beam like? You will get some kind of this, some kind of equation like this. Okay. So for this beam, like you can say, like instead of U, I'll say like W. W is the transverse uh, displacement. So this is the like uh, this is the governing equation of a beam. Okay. So in order to satisfy this, your governing equation should be 4 times uh, differentiable. Okay. So earlier the requirement was like uh, one time, but like 2 times it should be differentiable, like the strong form for a bar problem, because there was only like for a bar, the equation of motion will be like this, right? So for a beam, this will be a fourth, like 4 times differentiation happens to W. So here, here if we have a, let's say, a second degree polynomial, it was enough. But here, like the requirement has to be more. Okay. Now, and here also, first thing we have to note down is what are the uh, essential boundary conditions. So, can anybody tell me what are the essential boundary conditions here? This is for beam, not bar. Okay. You have like for bar only u is the primary variable. For beam, there will be two primary variables. Anybody can
U
guess?
0 equal to 0.
U is 0 at 0, and another essential boundary condition is there. Wants to want to guess?
U dash 0. 0.
Yeah, very good. So u dash at 0 is equals to 0. So while solving for beam problem, like u and u dash both are primary variables. Okay, in bar only u is the primary variable. Here u and u dash both will be primary variable. Sorry, here we are taking w. So w of 0 will be 0, and w dash of 0 is equals to 0. So both for a cantilever beam which is fixed at one end, both the deflection at the fixed end and also slope at the fixed end is 0. So if you take any, like if you want to assume some function, any function, like you can take some function which should satisfy both of these uh, boundary conditions. Okay, both of these essential boundary conditions. There is also natural boundary condition which has to be satisfied, that we should not care about while choosing the approximate solution or assuming the approximate. Let's say I'll take something like C2 plus C1 plus C2 x plus C2 x square plus C3 x. Will it satisfy? Will it satisfy my? Uh, will it satisfy my essential boundary conditions? Sorry, C3 and C4. Anybody wants to take a guess? Yes or no?
No.
No. Because if I substitute x is equals to 0 here, I will get C1 and other terms are 0. And d5 by dx uh, at x is equals to 0 has also be, has like that should also be satisfied, which will be 2 3 x plus 3 c4 x square. Okay. So if I substitute 0 here, I will get C2. So both the natural boundary, so both the essential boundary conditions are not being satisfied. Now I'll just like remove C1 here. I will remove C1 here, and I'll take C2x plus C3x square plus C4x cube. Okay. Will it satisfy these two boundary conditions, which is phi of 0 is equals to 0 and phi dash of x equals to 0? Will it satisfy? Only one it will satisfy. Yeah. This will satisfy only this phi of 0 is equals to 0. So that's why I cannot take this also as my approximate solution, because d phi by dx at x is equals to 0 will be C2. So I cannot take this also as my, like, because this is not satisfying both the essential boundary condition. So I have to refine it again. So finally I'll take phi of x is equals to uh, something like C3 x square plus C4 x cube. Will now this satisfy? Will it satisfy my essential boundary conditions, both the essential boundary conditions? Yes or no?
Yes.
Yeah. Because if you substitute 0 here, phi of 0 will become 0. And if you like do d phi by uh, d phi of x by dx at x is equals to 0, it will also become 0. Because this will be 2c3 0 plus 3c4 0 square. So this will also become 0. So essential boundary condition is getting satisfied. We can take this as our approximate solution, or we can assume this as the approximate solution. Okay, this is kinematically admissible. Okay. Now, instead of taking a polynomial, I can also assume some trigonometric function. Like, let's say I'll assume some function. I'll assume some function like this y of x is equal to uh, c naught c naught something like c naught cos by x by l minus c1 cos 2 pi x by l. Will it satisfy phi of 0 is equals to 0 and d phi by dx at x is equals to 0? So if you do d phi by dx, you will get uh, c naught into phi by l into this cos, right, minus sin x by l. This will become c1 into 2 pi by l into sin 2 pi x by l. Okay. Will it satisfy both of these boundary conditions? Uh, Essential boundary condition. Will this function satisfy that? Phi of x. Just substitute x is equals to 0 in phi, and also d phi by dx. Substitute x is equals to 0 and check and give me the answer. No, because if you substitute phi of like in phi of x, if you substitute x is equals to 0, you will get cos 0 is equals to 1. Here also cos 0 is equals to 1. You will get phi of 0 is equals to c naught minus c1. Okay. But here this will be satisfied. Like there is no harm on this. Second will be getting satisfied because sin x will uh, like if you substitute x is equals to 0, sin will become 0. So this is not getting satisfied, not kinematically admissible. So we cannot assume this as our approximate solution. Now let's take, I'll add this, whatever I'm getting here, phi naught is equals to C1 minus C2, or I can, let's say I'll add uh, C1, C naught plus C1. Okay. C naught plus C1 minus C naught into cos pi x by L minus C1 cos 2 pi x by L. Will this satisfy? Will this satisfy both the essential boundary condition? Yes or no? Yeah, because if you substitute phi naught here, sorry, x is equal to 0 here, you will get C naught plus C1, and you'll get minus C naught minus C1. So Cu naught plus C1 minus C naught minus C1, you'll get 0. And d phi by dx is already the same thing. So that will also get satisfied. So both the essential boundary conditions are getting satisfied. This is a kinematically admissible function. I can assume this as my solution for the brief. So this is how we will solve this. So like this is how we assume. Like whenever we assume a solution, we make sure that our solution is kinematically admissible. Okay. Now we will look into this problem where we will use variational principles. Okay. So uh, till now we have seen method of residuals, a method of weighted residuals. There is also another kind of there is also another method which we can use uh, to do approximate solutions, or like get approximate solutions instead of like taking the strong form, or like taking the governing equation. We can use this method also. Like in fact, this will be like more useful method. Like if you go into dynamics and different things. Obviously, weighted residual is also one method, but variational method is like very much, you can say, easier to deal if you have some complex problems, but we will see. So we have a bar we have a bar like this, so which is having this load of 10 kilonewton acting on the free end, and this is the proper these are the properties of the bar. A is 1000 newtons, 10,000 newtons, L is 1 meter, and now we want to like use variational formulation, develop the weak form, and we will assume some solution, and based on the assumed solution we will get the coefficients, and after getting those coefficients, like we will look what is the deflection of the bar at the tip, or you can say at the free end of the bar. So in variational methods, first we have to get what is the, like whenever you are solving any problem uh, using the variational principles or variational method, first thing we have to get is the total potential energy. We have to get the total potential energy of the bar. Or here we are taking bar like any structure, you can say total potential energy, and that can be given as like you will we will denote potential energy with this capital U kind of notation, and that will be equal to strain energy stored in the bar minus you can say the work done by the external force. So this is the total potential energy of the bar. So strain energy is nothing but, we have seen strain energy is nothing but strain energy, or you can also call strain energy per unit volume, right? So it is nothing but sigma into epsilon dV. So this is the total strain energy over the volume of the bar. Okay, and there is like work done by the bar. You can see that this force is acting in the negative x direction. So I am taking it as minus q, and into it is acting on the tip. So tip will have some like uh, so q is acting at the tip, so that I can take care by using this direct delta function. So direct delta function, I think you know. If somebody doesn't know, please tell me. I'll explain what is a direct delta function. So we use the direct delta function to write the work done by the bar, work done by the force on the external force on the. So now you can write, we can write by using the Hooke's law. We know that stress is equals to E into epsilon, because we deal with elastic deformations. Like throughout this course, we will deal with elastic deformation. I hope you know what is meant by elastic. It means the linear elastic case. It means the structure will come back to its original shape after uh, force is released. Okay. So that is, and also the deformations are very small. So that's why we are taking this. So we are assuming that deformations experienced by the structures are very small. Okay. And now you can see that because this is a like the cross section of the bar, I'll assume this has some square or rectangular cross section, and the cross section is same throughout the length. So now I can write this as 0 to L A into dx. So volume, I can write it as A into dx. Like if I have a small element, I can write the volume dv is equals to A into dx. Okay, I'll integrate it over the dome. So then I can write this as uh, plus q into, instead of taking plus minus, plus q into u into del x minus 0 dx, delta x minus. So for a bar, we know that because this is a axial force, or like it undergoes axial deformations, so we can take E is equals to du by dx, change in length, which is nothing but change in displacement by original length of the bar. So if you take it two times like epsilon square, you'll get. So we can write this as like this, du by dx whole square. So this is the total potential of the bar. Okay, so we have got this total potential energy of the bar. Now we have to make the variation of total potential. So because we are going for approximate solution here, like we will assume u with something else. So if you assume u is equals to something else other than like the actual solution, there will be always variation in the potential energy also, right? So because you are choosing u, because we are replacing u with u cap, let's say we are replacing u with u hat. So there will be some kind of variation in u, because you are not taking the exact u, right? So you are taking the approximate u, but we have to make sure that the variation of u should be zero when we take this approximate solution. So variation of potential should be zero. You, if you have taken some course on variational principle, you might be knowing all this variational calculus. There are a lot of things which you can learn. But for time being, you just like follow what I am saying. So let's say this is a variation operator delta. Okay. If I'm applying it on you, like this is something like you are applying differentiation. If you have u, like you can apply differentiation du by dx. But if you have, let's say, something like function of a function, so u is a function of x, and there is some other function which is a function of u, then you can call it as a functional. Okay, function of a function is called functional. Okay, so for these problems, instead of using differentiation, we use something called variation. Okay, so variation. Yeah. Just uh, like if you want to find out a maximum or a minimum of a function, what we do, we take the differentiation of the function and equate it to zero. We will get either the maximum or the minimum of the function. If you want to find out what is the minimum of a potential or minimum of a function, functional. So u is a functional here because it is a function of u. You can see it is a function of u. So now, if I take the variation of functional, if it is zero, then you can say that this is minimized. Okay, it is nothing but like it is very similar to minimum or a maximum of a function. A variation of a function, if it is equals to zero, that you can relate with that. Okay, so now I will take whatever you have taken here, and I will uh, apply variation on that. So variation of integral 0 to L E into du by dx whole square A into dx plus 0 to L q into delta x minus 0 dx. So this is my u. Whatever which we have found out is equals to u. So for whatever the solution which I choose, the variation of u should be equal to 0. So now I will apply variation like because this is a linear operator, I'll apply like we will see how we can do it. So if you do like if you apply variation, you can get this as uh, e into a into. So because this is like uh, differentiating twice, like you get like let's say if you have x 2x square, then if you differentiate it once, you will get 2x square. Similarly, you can get here 2 into du by dx to a, like this, and into sorry into d into del u by dx dx. So this is what you will get. And now to the if I apply variation to the other term, we are applying this like you can see we are applying variation only to u because u is something we are changing. So let's say if you have a bar and you are or bar or a beam and we have something like this. This is your analytical solution. But like let's say assume some other like assume some other if you are assuming some other function like over this whole domain there is some variation, right? That you can represent it as delta u. Okay, that is what delta u is. This difference over the whole domain is nothing but variation of u. You can take like lot of variations, right? Not only this, like you can like assume lot of solutions. Single solution, uh, like we can approximate lot of solutions. We can assume lot of solutions, and they will have some variation with respect to the analytical solution. So that is what delta u is. Okay. So this two and two you will get cancelled. Like no need to tell that. So and this will become the q into del u into del x minus 0 dx is equals to 0. So now we are getting this E into yeah anybody uh, okay u by dx d del u by dx into dx is equal to q into del of uh, x minus 0 into del u dx is equals to Yeah, this is equals to 0. Have to make this is equals to 0. Now, if you integrate this, uh, if you do the integration by parts here, you will get a e into du by dx. And if you integrate this, you will get del u 0 to L minus, we will get d by dx of a into du by dx, and there is also this, right? Del u plus 0 to L u into del minus, sorry, del of x minus 0 del u dx is equals to 0. Now I can write this. If I expand this, I'll get ae into du by dx into del u at x is equals to at x is equals to 0. Okay, minus. Okay, there is also like another term. First we have to do ae into du by dx del u at x is equals to L. So we have to remember that at the boundary conditions, at the essential boundary conditions, because at x is equals to L, at x is equals to L, our bar is fixed. At x is equals to L, our bar is fixed. That's why, okay, I'll write it. I'll write a into du by dx, just expanding. Okay. Okay. So you can see that because the bar is fixed at the right end, you can see the bar is fixed at the right end at x is equals to L. That's why at the right end, this del u is also 0. Okay. At this del u also equals to 0. So the variation of displacement at the x is equals to 0. So there will be some other terms, we will write them. So this will become 0. So that's why we will be remaining only with this del u. At the free end, there is some kind of force which is active. Okay. Some force which is active. This is at x equals to L. This is at x equals to 0. Okay. And you can send this here. You This is also like if you integrate this, you will get nothing but q into del. Uh, uh, this will become del u of 0, or you can say at x is equals to 0 if you integrate this, because this is a direct delta function. And we will remain with this only thing left, which is d by dx into va into du by dx into del u dx is equals to 0. So you can see that finally we are arriving at the same uh, thing which we have been looking at in the weighted residual. This is at x is equals to x is equals to L. Okay, x is equals to L. Sorry, x is equals to 0. Yeah. LU dx is equals to 0. So this is our natural boundary condition, which has to be satisfied. And this is our governing differential equation, right? So whatever is there, du by dx, our governing equation. So in order for this variation to be equal to 0, so these terms should individually should become 0. Okay. So because delta u is arbitrary, if you take any delta u, this integration should become 0. That means this whole thing should become 0. Du by dx is equals to 0. So this is over the domain, which is x belongs to 0 to L. And at x is equals to 0, this is our boundary condition, right? A into du by dx is equals to u. And at x is equals to L, we already know there is a natural boundary condition, which is uh, u is 0. Okay. Or u of L is equals to. So, like using the energy principle, or you can say variational principle, by minimizing potential energy, we are getting the same thing by the end. Like we are getting the strong form and also the boundary condition. So now you can see if you differentiate it again, like if you differentiate it by parts, so the uh, like by using the differential, by using this whatever we have got, we can again integrate this by part. Like the strong form which we have got, we can write this as this. So delta u, let's say delta u, you can like you can also take delta u as well w here. So we can convert this again into a weighted residual problem. So w or delta u, nothing like makes a difference. Okay, both are like same things. So we are getting this. Now I am assuming some approximate solution u instead of u cap. Okay, and I am taking w bar, and there is some boundary condition which is also applied, natural boundary condition, and it is at the uh, uh, x is equals to 0 end. Okay. So now if I do it again, the integration by parts. So if I do the integration by parts again here, I'll like finally end up with uh, and also I will assume w is equals to w bar. Like we can do that. There is no problem. Okay. If I assume w is equals to w bar, and let's say we will assume u is equals to n u cap is equals to n1 u1 plus n2 u2. Okay, this is some kind of approximate function. Like n1 and n2, we have to like let's say we have to assume something. Okay, this is nothing but Lagrange interpolation kind of thing. Like we have already seen Lagrange interpolation. So so u1 and u2, u1 and u2 represent the left displacement and the right, or you can say displacements at uh, left hand and right hand of the bar. Displacements at left hand and right hand, respectively. Okay. So here, if you do like if you do the integration by parts, you will get this. Finally, we will get this form. We have already done the integration by parts. So you will get this. Okay. The Q is equals to 0, W into AE into du cap by dx is equals to A. So now we will substitute U cap is equals to N1 U1 plus N2 U2. And let's say we will assume first we will use the Galerkin's approach. So in Galerkin's approach of weighted residual, Galerkin's approach, we will assume whatever the basis functions which we are taking, we will take them as the weighting functions also. So we will take W is equals to N1 first. So after like substituting W is equals to N1 and substituting U is equals to N1 U1 plus N2 U2, we will do the approximations and you will get this equation. Okay, I am just writing simplifying. I'm not simplifying it. I am just writing. Okay, like after substituting W is equals to N1 and U cap is equals to N1 N1 U1 N2 U2. Okay, and here I will get this again dnx by dn2 by dx u2 dx n1q x is equals to 0 minus n1 into ae into d of u by dx at x is equals to 0. So this is one weighting function we are taking. Similarly, because we are having two coefficients right here, u1 and u2, so we have to get two equations. In order to get another equation, we will assume W is equals to N2 here. So same thing, instead of the W is equals to N1, we will assume W is equals to N2. We will get some other equation which will look like this. So let's say this is equation 1, okay? Equation 1. Equation 1. Substituting U cap is equals to N1 U1 plus N2 U2 and W is equals to N2 in equation 1 or weak form, you can say, or weak form. You can say again, you will get something like this. Same thing with a minute difference. And here, instead of N2, we will get, instead of N1, we will get N2. So this is x equals to A. So now, integrating polynomial, whichever we are taking here, this is both are x is equals to, this is x is equals to 0 and this is x is equals to 0. Okay. This is x is equals to 0. So whatever the integrating polynomial which we are taking, n1 and n2 should satisfy the essential boundary conditions. That is the kinematical admissibility which we were talking about. So n1q at x is equals to 0 from the, let's say this is equation 1, sorry, this is equation 2 and this is equation 3. So from 3 and 4, and these two things should become 0 because n1 and n2 should satisfy the essential boundary condition because the bar is Sorry, this is the x is equals to L. Yeah? X is equals to L. X is equals to L, and this is x is equals to 0. This is x is equals to L, and this is x is equals to 0. Okay. Minor change. At x is equals to L. Okay. And uh, this should also become 0. N1 into du cap uh, uh, at x is equals to 0 we are taking. So this at x is equals to 0 will become equal to 0. And N2 into AE to du by dx. Sorry, this think I have messed up. Yeah, it's fine. Du cap by dx is equals to at x is equals to 0, and this will be equal to our q, whatever we take. Okay, so yeah. So whatever we are like whatever the values which we have got, we will substitute this uh, uh, into equation 3 and 4 in equation like 2 and 3. From 2 and 3 we will get from 2 and 3 we will get two equations, and two equations I can write it as a matrix form that can be written as dou n1 by dou x, sorry, d11 by dx, dn1 by dx integral 0 to L dn by dx dn2 by dx dn2 by dx dn1 by dx dn2 by dx dx is equals to, at the free end the force is q, and at the this is at the uh, what do you say, this is the fixed end. This is actually becoming 0, so we don't need to take care of that. Now we can assume n1 is equals to 1 minus x by L. So n2 is equals to x by L we can assume. So if you put this, like you can see that n1 u1 plus n2 u2, right? Uh, so this can be taken as this x by L, x by L. So now you can see that if you put x is equals to L, uh, u2 is like known to be 0. So if you put x is equals to L here, the essential boundary condition will get satisfied. So this approximate solution will satisfy the essential boundary. And so if you differentiate n1, you will get minus 1 by L. If you differentiate n2, you will get 1 by L. And if you substitute in this matrices, you will get finally this equation, which is a matrix form 1 minus 1 minus 1 1 u1 and 0 is equals to q into sorry, q minus uh, a into du of x. This is at x is equal to 0. Sorry. We will get this. So u2 is already known to be 0, right? Because this is a fixed and u2 should be 0. So therefore, finally, we will get, if I solve this matrix system, like you can see, whole problem, which was integration, has been converted into a linear algebraic equation. So this is a matrix solution which we have to find out. Computers, like if you write a code, computers will do it in a very efficient manner because you are already assuming the solution and you just want to find out the coefficients of that solution. So instead of doing the integration, the whole problem has been boiled down to a algebraic equation. So solution of an algebraic equation. So that is the advantage of using this approximate methods, or eventually, like we will talk about finite element method. So that has also been discussed in this week, but we will look at in a very detailed manner in the next class. So u1 is equals to minus ql by ae. Finally, we are getting. So u1 is nothing but uh, we will have uh, this equal to you can say this is x is equals to l. Sorry. Yeah. If you substitute q is equals to 10,000, 10,000, right? Yeah. 10,000 newtons. And if you substitute L is equals to 1 meter, and if you substitute A is equals to 10,000 newtons again, you will get the deflection of bar is minus 1 meter. So whatever the load which we are applying here, this is U1, this is U2, U2 is 0, and you are applying some force Q, is 10,000 newtons. If you apply this load on this bar, you will get deflection of minus 1 meter because you are applying this in a negative direction, negative x direction. You will get negative elongation, which is minus 1. This is like very high, but not practical, but yeah, not very big issue. So this is how we will solve our our problem using approximate solutions or approximate approaches. This is the Galerkin's approach. So first we use the variational principles to get the strong form, and then we derive the weak form, and from that weak form we assume the solution. Some solution we assumed, and we substituted the approximate solution. And after substituting the approximate solution, we will get some equations. So we can assume W, which is the weighting function. We will assume W is equals to N1, N2, whatever the basis functions which we have taken. We will get two equations and we will have two constants, right? U1 and U2. So we can solve for that and we will get the solution finally by solving this matrix equation. So like whole problem has boiled down into a matrix form. So that is like very useful if we are solving something with the help of computers. So you assume the solution and tell the computer to find out what are the coefficients u1, u2, u3, something like all these coefficients will be found out. So this is the solution to this problem. I hope you have understood. Like go through this problem again. I'll share the link will be shared with you. Like you can, I hope you know where to find these links in the course module. There will be at the bottom you will see a link problem solving sessions. If you go and open to that, you will be directed to a Google sheet. In that you can look at this. Okay. So any doubts with this? Uh, Any doubts, or are you clear with that? Or if you have any doubts related to the assignment questions which have been given to you, have you solved the assignment? Anyone? Anish, Amrita, Janet, solving. Okay. Hello.
Hello,
Uh,
sir.
yeah, am I audible?
Yes, sir. No.
Uh,
Sir, in the assignments there, in that in the system
yeah.
there, springs are shown, sir. How we'll take that into account for the solution?
Uh, I didn't like. In which question you have that? In which question you are confused?
I think in all the problems, in that along with the bar
Hmm.
element, one spring also is connected. In some case, it is in
Yeah,
series.
yeah,
Some I think
yeah.
it's parallel.
Okay,
So how we'll take that into account?
okay. So let's uh, like you. I will suggest you to the variational. I will suggest you use the variational approach. Okay. So like you will have something, right? Let's say you have something like uh, bar problem. Let's say this last question is there, which is question one. You have to see. Question one is like very simple. You can just look at it and guess, but uh, we will see. Okay. I'll I'll explain the last question. Okay, I'll explain the last question. I will not solve it fully, but I'll give you an idea. So this is the bar, and there is some spring attached to the bar. And at one end of the spring, there is a force acting. Okay, and there is the stiffness of the spring is K. And the bars, like one end of the spring will undergo a displacement U because of this force is applied, and other end, which is connected to the free end of the bar, will have some displacement UB. Let's say uh, this, yeah, this will be UB. Okay. Or better, what we can do is like in order to avoid confusion, you can take this as uh, yeah. Okay, we will do it. So no worries. So so there is like lot of like you can take a lot of approaches to get the differential equation. But the easiest I will suggest you to go through is like whatever we have looked at is the potential energy or like the variational approach. So energy approach or variational approach. So in that, like you can define the potential energy or like phi or u as because there is a bar and there is also a spring, right? So there is a bar and there is also a spring. So the total potential energy phi, or let's say You can call it u only. This will be integration 0 to L EA into uh, du by dx, or let's say here, in order to avoid confusion, I'll call it as w. Okay, I'll call it as w, dx whole square dx plus half into u minus ub half into k into u minus, because there are like, the spring is not fixed at one end. This end is also moving and this end is also moving. So total extension of the spring will be u minus ub. So like this end will move this much, and let's say if this end is moving like this much. So if I subtract this from this, I will get the total extension of the spring. So half into k into total deflection of the spring, or you can say delta x also you can say. So total deflection of the spring square will get the total potential energy, total strain energy stored in the spring. This is the strain energy stored in the bar. This is the strain energy stored in the spring here. Plus there is also a force which is acting, right? So for that force, I write as half into q into, or you can say like, let's say I will write this as q into u, because this is acting at this end, right? On the free end of the spring, I'll write it as this is the force which is acting on the system. Like this is the work done by the force, total work done by the force. Okay. Now, if you apply the variational approach and proceed, you will get the strong form of the equation. So you take delta u is equals to 0. You apply a variational formulation, like variational, how I have solved, like previously how I have solved, you do it. So here, remember that you have to take delta w, okay? Because this u and this u are like both confusing. I am taking w here. So deflection of the bar is taken as w here, okay? And you also take this ub is equals to delta ub is equals to w of l, and u of w of 0 is also 0 here, because the fixed end is not moving anymore. So like using the previous approach, you apply the variational and do all the simplifications, do the integration by parts, you will get the strong form of this equation. Okay. Simply, we had also this problem, right? I think the first problem. First problem. So there is a spring acting here. There is a spring here, and there is some force acting. Okay. So now I can take the total potential energy as half into 0 to L. Let's say I'll take U only here, E into, because there is no confusion, E square plus the spring is undergoing some this because the force is being applied. The spring will also undergo some kind of this spring will also store some energy, which will be equal to half into k into u of uh, you can say u of L square, like this. You can write it as u of L square. And there is a force which is being applied. You can write it as integral q into uh, u into del of x minus L into dx. 0 to L. this will be nothing but q into, like if you integrate it, you will get q into u of l. So I'm writing this as uh, this thing because like you will get, like it will be easier to do. So if like, and also you can also write this, yeah, this is fine. Like if you integrate this, like if you apply the variational to this, apply the variational, like delta phi, if you make it equals to 0 and you solve it, like whatever we have done, do integration by parts. If you do it, you will get the governing equation, like, and then you can solve like first question and also the second question. You can do it without any trouble. That you can do. It's not a big problem. Yeah. You can also write this variational also. I think you can, yeah. U of x, this also we can take variational. This also take, this also we can write it as delta of uh, x minus l. So now you can like do your, like this also you can take like this. Okay, this will be the form. You apply this variational, make it 0, you will get the answer. It's not very hard to do. Okay. Yeah. You will get the first and second, and third also you can solve. Uh, third also you can solve like whatever the Galerkin approach which we have used, you can use that and solve the third also. And fourth is something which I'll explain in a simple manner. Like let's say if you have two springs, okay, two springs, and they are like connected like this. They are connected like this. These two springs are connected in series, right? Yes, sir.
Yes, sir.
Now let's say if I apply uh, some force Q at this point. Okay. Now let's say if I have instead of this, I'll have this arrangement. Like springs are connected in parallel. Now I'm applying this uh, force Q. Okay. Is there any difference between these two? Is there a difference? No, there is no difference between this. Because if you see here, this configuration is also equal to this is also equal to springs connected in parallel, because you can see here at this point, if I apply a force Q, how much ever the displacement this spring like undergoes in tension, this spring will undergo the same kind of displacement, but in compression. Here, both the springs also will undergo same kind of same amount of deflection, but in tension. Whenever the springs undergo, like whenever two connected springs undergo same deflection, they are like they can, you can consider them to be like connected as parallel. Okay, so because like here both the springs are undergoing same deflection, that is x, let's say that is x, or delta x you can say. These two springs are also, you can say that these two springs are also connected in parallel, or like you can say this is equal to this. So this, both these systems are like similar, you can say, because you have these both these springs, and if you like, if you want to find out what is the, like let's say force at this, let's say I'll take the force equilibrium at this one, at this connection of the springs, point of the connection of the springs, then Q should be equal to whatever the spring which is experiencing. Let's say this first spring is experiencing tension. I'll write it as uh, like F1, and this another spring is undergoing, let's say deflection. Okay. So substituting like whatever you get here, you can write this as Q1, sorry, Q is equals to, uh, because this is undergoing delta x. So first spring will undergo delta x, and the second spring will also undergo delta x, but in negative direction, right? So that will be negative delta x. So that will be equal to k. Sorry, this is into k into k2 into delta 2. So that will be equals to k2 into k1 plus k2 into delta x. And you can say I can write this as k equivalent into delta x, right? So you can, or you can write this as k equivalent into delta x, which is equals to k equivalent into k1 plus k2 in delta x. Finally, you will get k equivalent is equals to k1 plus k2. Or you can also write delta x is equals to q by k1 plus k2. So force by total resistance or total stiffness of the springs will give me the deflection. So total stiffness of the spring, you can see I am getting by adding the stiffness of each springs. In this also, we will get the same answer. Delta x is equals to q by k1 plus k2. So these two springs, these two conditions are same. But instead of this, let's say if I have two springs connected like this, k1 and k2, and if I have a force applied here, not instead of the middle point, if I am applying it here, this will not be equal to this, because here the springs are connected in parallel, and the deflection which this will undergo will be different than this, because the two springs will have different stiffnesses, but the total force along the system will be same. So that is series connection of springs. So using this, you can answer this question. I think question, what is it? Question 4 you can answer. Question 4, like question 1 and question 4, they are saying to compare question 1 and question 4 and answer something. But if you like, you can look at this, you can answer the question 4. So I won't give you the direct answer, but now you, I think if you uh, are able to understand, you will get it. Okay. Okay. So these are all the, like you can get the answers, like I have told you the approach, you follow that and you will get. So it's not a big deal. Uh, you follow the approach and you will get all the answers, like first, second, all these things. So I think uh, today we will close it. Do you have any other doubts to ask? If not, we will close the class for today. Anyone? Okay. Okay. Hope the session was helpful. uh, and hopefully you have learned something. And like if you have any doubts regarding the assignment which you are solving, like you can, like whatever you have solved, you share with me, like this is how I have solved, and this is something which you are getting. You can write me a mail. You have further doubts, I will surely try to help you in every way possible. Okay. So, but you try it, because I'm not supposed to directly solve whatever the solutions I have been instructed. Like I should solve some other problems similar to the problems, but I cannot solve the same assignment problems which are given. Okay. So write me a mail whenever you have any difficulty related to the course or something else. You can write. And some other is like I just wanted to ask if anyone is working in the field of dynamics. Like a lot of you are PhD students, right? Uh, I just wanted to know if you are working in the dynamics. Uh, you are you like any one of you working in dynamics, like dynamics or nonlinear dynamics, or you are planning to work uh, in this direction? Anyone? I have something to share. Nobody? Okay. Okay. So what I'll do one thing. I'll share something with you. There is a Gian course which uh, is being organized by our lab, like the lab which I'm working in. There is a Gian course which we are conducting. I think from 20th, uh, 25th of this month to 30th, I think. So this GN course is on energy harvesting. Okay. So energy harvesting is nothing but you take the vibration of a system and uh, convert that vibrational energy into energy, like electrical energy, and do uh, use that energy to power some sensors or something which like so that energy can be of some use, right? Like a lot of vibrations occur in machines that can be used, otherwise goes wasted. But whatever the vibrations which we want to whatever the vibrational energy which we want to analyze, like that is a very difficult problem, like and also very interesting. So that is like entirely non-linearly dynamical system. And analyzing dynamical systems is a very huge task. So harvesting energy is fine, but like the main problem is to analyze the dynamical system. So if anybody is interested in nonlinear dynamics or just dynamics, you can go through this link which I am sharing in the chat. Or if any one of your friends is interested, you can suggest them to go through this brochure which is there on LinkedIn. And if you want to if they want to join the course, like that will be conducted in IIT Madras.